Yes, sir. We'll start.
Yeah. Can you hear
Uh,
me, madam?
yes, sir. We can hear you, sir. So we'll be having a second session of the day on nanophotonics. I request Professor Sapna to introduce our chairman, Dr. Vaibhav, M, to the participants.
Ma'am, slides are visible?
Yes, sir. Slides are visible, sir.
Hello, good morning. Now we will be starting with our second session. This second session will be taken over by Dr. Vaibhav, currently working as chairperson, Dayanand Sagar University in the Department of Electronics and Communication. To name a few of the achievements of Dr. Vaibhav, Sir pursued his PhD from BITS Pilani. Sir also chaired many sessions in national international conferences, journal chapters, and also was a renowned speaker in many of the sessions on various topics. A special interest of Sir are digital signal processing, signal system, VLSI, CMOS, to name a few. The very notable recognition of Dr. Vaibhav is he got the Employee Recognition Award at Philips Semiconductor and also Best Technical Support Team Awards in HP when he was into industry. In academics, Sir has many of the papers on his name and also a very noble professor where students also are very much fond of Sir's lectures. So, sir, we are very honored or we are very glad to have you and hear from you, sir. Please, you can start the session. All the participants are eagerly waiting to hear from you, sir. Thank you.
Thank you, Sapna madam, for the introduction. I hope my voice is clear to all of you. I will try to speak louder. There might be some problem in my laptop, but I will try to speak louder. Is my voice audible, Nandini madam, Sapna madam?
Yes, sir. It's okay, sir.
Yeah. So today this session, this FDP is for disciplines in nanophotonics. So I would like to talk on nanotechnology and how the nanophotonics is working in that domain. In that way, I would like to talk. So the presentation will be that what is nanotechnology, why we are talking now about nanotechnology, why length scale is so important, nanotechnology sector applications, electronics and the modern world, taxonomy of nanoelectronic devices. Taxonomy of nanoelectronic devices means what are the devices that we'll be seeing in the future, which should not be shocking for you when you are heard the name, when you are hearing the name of the devices. To understand all these nano devices and all, we will be talking of the quantum confinement. Now, what is this quantum confinement and all? I will be discussing when I will be coming to that particular topic. What is photonics, nanophotonics, and electron-photon confinement? All this, after understanding all these things, you can proceed in the direction of the quantum entanglement, quantum computing, and all this. Because the coming era, we are seeing is belongs to the quantum entanglement, quantum computing, quantum physics, and all. So I will try to explain all this phenomenon in a very short duration, 1.5 hours. I will try to see that most of the fundamentals are getting clear here. Because if the fundamentals are clear, then you can start working in that direction. Some of you might have already known this, or no, some of you might have already known this facts. For some of you, it may be a very new thing. But this is what is the era that is coming up. So going ahead, okay. If we see this thing, this is something called it's not an interactive session. So I can say this is a hardware drive. This is a 5 MB 5 MB IBM hardware drive, which was in 1950s. Now, if we see today, if we go ahead with the same technology, this is a hard drive. This is a hardware. This is a hard drive. This is a IBM hard drive, which is just 5 MB, which was in 1950s. If we go ahead with the same technology today, you can assume that how much space will be required for the drives and for the memory. Let's take an example now. If I am talking here, we at least have 1 GB in our pocket at present. On an average, we might be having 1 GB on our pocket. We have a mobile phone with a 24 GB. If we go ahead with this 1 MB sort of a hard drive, then imagine how much 1 GB will be required for storing it. So what happened? Because to overcome this technological hurdle, people have started reducing the size of the devices. That means this hard drive might have been manufactured using vacuum tube and all. You might have seen how the vacuum tubes and all looks like. I will show it in further slides too. So this hard drive was manufactured using vacuum tube. If you try to use this vacuum tubes and all this thing for manufacturing, imagine how much 1 GB space will be required. So there was a requirement to reduce the size of the devices. There was a requirement to reduce the size of the devices. So it went on from a centimeter to millimeter to micrometer, and from micrometer to the nanometer. Now whatever the devices that we are talking today are in the range of nanometer. So nanometer is also a unit of meter. Centimeter is also a unit of meter, and micrometer is also unit of meter. So when we are trying to reduce the size of this device, we have to reduce the size of the device to see that our devices are getting fit into 1 GB. When we are trying to reduce the size of these devices, when we are trying to reduce the size of these devices, we are going from a micrometer to the nanometer. If we are not doing this, we are not going from a meter to a nanometer range, we will not be able to fit all the devices into a single chip. We will not be able to fit all the devices into a single chip. This we have to keep in the back of mind, that nanometer is the coming in. So if this was the hardware drive in the 1950s. Now, what is nanotechnology? It is something nano plus technology. It is in the range of 10 raised to minus 9. Now, how this nano and photonics is getting combined, that I will try to explain it. But before that, when we are trying to reduce the size of a device from micrometer or from a meter to a micrometer or from micrometer to a nanometer, there is a huge lot of paradigm shift. I would like to explain this with an example. Suppose we have a tennis ball with us. We hit a wall. If we hit a wall, what is our general reaction? That ball will be, because of the third law of Newton, the ball will be reflected back, or the ball will be coming back. Every action there is an equal and opposite. But if it so happens that this ball is passing to the wall, then we will try to find the answer to this question, that why this ball is passing through the wall. The answer to this question is not in a classical, because classical physics, and that is a Newtonian physics and all these things. If you try to understand the phenomenon, that why ball has been passed and why the ball has been passed, to understand this. One second. Okay. Now, if you try to understand this phenomenon, why this ball is passing through the wall, if you try to apply the classical physics, you will not get the answer, because the classical physics is that to every action there is an equal and opposite reaction. To understand this phenomenon, we have to move to the quantum physics. Now, quantum physics works on three principles. The principles are quantization, Heisenberg's uncertainty principle, and wave particle duality. So waves can only pass through the wall. So at that particular 10 raised to minus 9, that we call as the nanotechnology, nanophotonics, and whatever the nano we call, that's the range of 10 raised to minus 9. Now, what is the great thing about this 10 raised to minus 9? 10 raised to minus 9, when we are trying to reduce the size of the devices and taking it to the 10 raised to minus 9 level, that means we are taking material to the 10 raised to minus 9 level. At that time, we are coming to the domain of a light. 10 raised to minus, in my next slide I will show you that light is also having the range in the 10 raised to minus 9. We are coming into the frequency range of the 10 raised to minus 9 is also the frequency range of a light, that we pure and violet, indigo, blue and red. Now, when we are going to the 10 raised to minus 9, which is the domain of light, which we call it the photonics and all these things, we come across very certain, very strange phenomenon. The strange phenomenon is that that electron is behaving as a wave as well as particle. The electron is behaving as a wave as well as a particle. Going back to the earlier example, that how the ball has passed through penetrated through the wall, because the electron might have, or the ball might have converted it into the wave. So it has passed through the wall. That is called a wave particle duality. This can be understood. Now, when we are going to the 10 to minus 9 regime, this is the regime of a light, and we know that light is a wave as well as a particle. Light is a wave as well as particle. Particle we call it as a photon. There are a number of the experiments conducted to understand this phenomenon, the very infamous experiment or famous or infamous experiment is a double slit experiment. You can make a note of this thing, double slit experiment. You try to get more knowledge on this double slit experiment. But this double slit experiment cannot be understood if we are applying only classical physics. This double slit experiment can only be understood if we are applying the quantum physics. So there is a huge paradigm shift here. If you wanted to understand the phenomenon at 10 raised to minus 9 level, that is nano level, you want to understand the phenomenon that are happening at the 10 raised to minus 9 level, we have to move to the quantum physics because answers are not there in the classical. Classical physics, that is only Newtonian physics, Newton first law, Newton second law, all this. If we try to, this is the very fundamental, if you move to the nano level, very fundamental thing that we need to understand, we can move to the nano level, that we have to apply the quantum physics. We have to move from the classical physics to the quantum physics to understand the phenomena that are happening. I will tell you with the example in the upcoming slide to understand the phenomena that are happening at the nano level. If we don't go to the nano level, then go back to my example. We cannot have 1 GB memory card in our pocket. If we don't have, we are not reducing the size of it. We cannot have a 1 GB memory card in our pocket. Almost we are sitting here, we are listening to the lecture. On an average, we might be having 3 GB or 4 GB in our pocket. We cannot carry this. So we have to reduce the size of the device. When we reduce the size of the device, then we go from the meter to micrometer to the nanometer. When we are going from the micrometer, meter, micrometer, and to the nanometer, we have to move from the classical. We have to move from a classical physics to a quantum physics. And what are the principles of the quantum physics? Principles of quantum physics works on a three principles. That quantum physics works on a three principles. That is Heisenberg's uncertainty principle, because we don't know where the electron is. Where the electron is, we don't know. First is Heisenberg's uncertainty principle. Second is a quantization, and third one is a wave particle duality. So moving ahead, we'll try to use this to understand the phenomena that are happening to to understand the device, to understand the nano device, we have to understand the quantum. There is huge paradigm shift here. The paradigm shift is from the classical physics to a quantum. So to understand next line is there. So it is 10 raised to minus 9. Whatever is the 10 raised to minus 9, it is a 10 raised to it is a 10 raised to minus 9. The device size we are taking is 10 raised to minus 9. But okay, these are the general, but technology means discipline and all this. We have more interesting slide. So this is what I have spoken already. So if you see the structure, it is somewhat like this. The 10 raised to buckyball and all these things. These are in the range of this red blood cell in the range of the 10 raised to minus 6 micron. Buckyball is in the range of the 10 raised to minus 9 nanometer, 10 raised to minus 9 times. So you can see this DNA structures and all this to make you feel that how the 10 raised to minus 9 will be, the 10 raised to minus 9 level will be there. So carbon chains are on this 10 raised to minus 10 raised to minus 9 and 10 raised to minus 9 is the nanometer. We have to go to that range. If you are not going to that range, we cannot carry, as far as our electronic systems and our electronic systems, we cannot carry 1 GB now. If you go ahead with the vacuum tubes and all these things, imagine the size of our laptop, imagine the size of our computers, and imagine the size of our TV. Then we make our whole building to, if we are trying to manufacture, using the vacuum. That's what we have to do to 10 raised to minus 9. But when we move to the 10 raised to minus 9 level, again I am repeating, there are certain challenges. What are the challenges? What are the questions that has to be answered? What are the challenges that we are facing that can be answered only using the quantum physics? Now, going at so many scientists view nanotechnology as a revolution technology of 21st century, just as plastics will always say. Similarly, we have seen the nanotechnology. Nanotechnology products are currently using more than consumer products. Okay. Size matters. Okay. Nanotechnology is based on the method that is so small that it exists in the atomic level and the molecular level. If we are going to the size where it is in the atomic or the molecular level. At this size, the substances, physical, chemical, and biological properties are changing, and this, by harnessing these new properties, researchers have found that they can develop material, device, and a system that are superior to those used. Now, what happens when we are going to the 10 raised to minus 9 level? If you are going to if you are taking material to that level, 10 raised to minus 9 level, either it can be inorganic or inorganic. You are taking to the material physical properties. Physical property will change means one that if we have a copper which is in the centimeter range, it is very well a good conductor of heat, good conductor of electricity and all this. But when we go it is acting as a but when we go to the, if we cut the copper into the pieces and keep on cutting it, and we take it to the nano copper range, it won't act like a copper, but it will be it won't act like a bulk copper. At this nano scale, the story of the copper will change. That change in the property of the copper. Now copper may not be that we need to investigate. That copper may not be a good conductor of electricity, or it may have some other properties. This change in the properties we are taking, this change in the properties will be using it for our advantage. If you take the copper to the nanoscale level, we can have nanotubes and all these things, which is the strongest material known in the world actually. So the change in the properties, this change in the properties of the copper, we are using for our benefit. One example I would like to put here, that suppose we cannot mix petrol and we cannot mix oil and water here, because there's specific gravities to it. But by chance, if we take this oil and water to a space, yes, there is no specific gravity. These two liquid they get mixed. These two liquid they get mixed, and it may create some another material which may be beneficial for our human being. So there is a change in the property of the material which we are using for our benefit, and that benefit which we are changing it for our benefit. As we, with all practicality, all scientific breakthroughs, nanotechnology carries both risks and carries both risks and reward. Will be more looking into the reward side. So while it appears almost certain that the rewards will greatly outweigh the risk, attention must be paid to possible dangers to the well-being of the human. So we'll try to, whatever this change in the properties of the material are there, we'll try to see that we are using it for the benefit of the planet. So I will quickly go through the sector application. So it is not only nanotechnology is not only applicable for our electronics, it may be for automotive, for the construction, for the electronics, for engineering, for food, medicine, and there are so many applications. There are so many applications where nanotechnology can be applied. Each and every sector can then take the advantage of changing the property of the material. So nanotechnology for the consumer products, these are some consumer products that nanotechnology is used. But this is not a part of our discussion here. Our discussion will be on how the nanotechnology will be used in the electronics. Now the question comes, we are talking so big into the nanotechnology side. We are saying that nanotechnology is coming up, nanophotonics is there, nanobiology is there, and so many, each and every field it is applied. But now the big question comes, why now only? Why it was not earlier? So why now? It seems that nanotechnology has begun to blossom in the last 10 years. This is largely due to the development of the new tools and instrumentation for the nanotechnology that allow researchers to observe and manipulate the matter at nano level. Now it had come now because we have the instruments, we have the tools to observe the phenomenon at the nanotechnology level. And now here again one example is there. We are studying Fourier transform, Fourier series, and Fourier had come up with the Fourier transform, Fourier series since 300 years. But the actual calculation of the FFT and all, it has started by coming up with the good computers, and coming with the MATLAB and all. It doesn't mean signal processing. It means that signal processing is using Fourier transform. It doesn't mean that the Fourier transform equations were not solved earlier. They were solved earlier, but the phenomenon that can be observed using MATLAB or using another tool, using MATLAB or using some other tools, the computation speed had been increased by using the computer. This is one example that how tool had helped us to understand the Fourier transform. Because we have the faster computers available today, the faster computers are available today. The faster computers are available today, we can do the FFT calculation faster. Early in the older days, in the 90s and all, if you wanted to calculate a Fourier, now also those who are studying Fourier series and Fourier transform in this PSP, then if you knowing how much efforts are required to calculate a Fourier transform, n is equal to 10. It's very difficult. But with the coming of the computers and all these things, we can understand the Fourier transform, we can do the analysis related to wave, we can do the analysis related to we can do the analysis related to it. It was easy to understand. So that's why invention of a tool in the last year, new development tools had come up to understand the phenomenon at the nanotechnology, which is not available, which were not present in the earlier time. So that's why we see so much research and so much activities happening in the nanotechnology. Now, what are the tools and what are the instruments that are coming up? Tools and instrumentation for nanotechnology. These are the scanning electron microscope. Tomorrow you should not is surprised that in your lab the instruments are replaced by scanning electron microscope, transmission electron microscope, scanning probe microscopy, or scanning tunneling microscopy, atomic microscopy. So these are the instruments to observe the phenomenon at the nano level. Now, again, why now? Again, to answer this question, why now? Just as Galileo's knowledge was limited by the technology in his day, until recently, a lack of good instrumentation prevented the scientists from getting a more knowledge of the nanoscale. As you are aware, that Galileo was going to observe the phenomenon happening onto the space with the telescope. Earlier, before Galileo, it was assumed that Earth is a planet. And when Galileo observed through his telescope and all, he come up with the idea that Earth is not a planet; it may be spherical or it may be round in shape. And for making that statement, he was put behind the bars. He was kept under house arrest because the general belief was that Earth is a planet, and he was making a statement that the Earth is not a planet, it's spherical. But Galileo was right at that time. He was having some instrument, a telescope, to observe the phenomenon, and on the basis of that, he could make the statement. We can say in early 90s and all, we were not having that instrument to observe the phenomenon at a nanoscale level. So there might be there was a restriction to go to the deep. But now we have that instrumentation, we have that tool to observe the phenomenon at the nanoscale level, and we have the research nanoscale. We are going research the nanotechnology, and it is not related to any specific field. You can use this nano in any and all the field. But the thing that has to be remembered is that here we need to understand the thing. The nanotechnology, we have quantum physics. As a basic instrumentation for observing, manipulating, and measuring event at this scale are developed further advances in our understanding and ability to do. Now, when God plays around with that nanoscale, change the rules of it. And human beings start to take the advantage of God's favor to use the particular properties of a nanostructure in application of manufacturing of the material for medicine. They have taken the advantage of some properties are changing. This change will have properties of the material with a 10⁻⁹ level. Properties of the material are changing, and this change in the property, whether it can be used for our benefit, either it can be used in the medicine, or it can be used in some industry, or it can be used in some decoration or environment that we are looking at. So now this was my general discussion on to the nanotechnology and all this thing. Now we'll see how it end up being. No voice. Hello. Are you hello?
Yes, sir, we are able to hear you, sir.
Okay, fine. Hello, are you able to hear me? Hello.
Yes, sir.
Okay. Okay, fine. So there was some technical glitches. Sorry for that. I hope you are. Yes. Okay. Are you able to hear me, ma'am, Sapna madam?
Yes, sir.
Yeah. So the 21st century was transformed by. Now we will move towards our particular. We will move towards a specific our domain, that is an electronics domain. And the 20th century was transformed by the electronics and microelectronics. Electronic systems were built with the electronic devices. The most important one is the transistor. Now I will try to tell you why we are moving to the nanoscale level. The nanotransistor is the first true active nano device. We will move to the nano transistor now. So the history of the electronic devices, it starts maybe 83 with a vacuum tube, and that IBM device that I had shown it to you, it was using the vacuum tube. Then came up the diode, and then we moved to the triodes in 1905. And then we moved to this was the computer that was manufactured using the vacuum tube in 1948, using the in 1948. Then came the transistor, which was in 1947, and then field effect transistor in 1945, 1925, and in 1925. So this is some sort of a taxonomy of nanoelectronic devices. Here we have a nanometer scale of electronic switching. One is we will try to understand the devices that are based on quantum effect, nanoelectronic devices. These are further classified into solid state nanoelectronic devices and molecular electronics. We'll not go into the detail of molecular electronics. We'll try to understand what are the solid state nanoelectronic devices. So going ahead, we can say these are the devices. That is solid state nanoelectronic devices, which we will be looking into and which we'll be studying in our which we'll be using in our application, which we'll be studying in our curriculum. Like here I would like to give an example, like our diodes, like our vacuum tubes and all. Nowadays we are not studying vacuum tubes and all. Probably we have in our curriculum we have field effect transistors, we have field effect transistor, but we don't have vacuum tube and all. Going ahead, and the way the research is happening going ahead, you can see that quantum dots, resonant tunneling devices, single electron transistor, these are the devices that you will be studying, and most of the application or all of the applications will be based on the you cannot rule out completely FETs, we cannot completely rule out transistor diode, but it may be the combination of these quantum dots devices, resonant tunneling devices, single electron transistor devices. We need to, when we try to understand any device, we need to understand the physics behind that. When we try to understand the physics behind that device, like suppose if I say what is PN junction that is. So you cannot say that P and N junction. We need to understand the understanding of the device. PN junction device will come to the understanding of the device physics, and to understand the device physics, we have to understand the energy band diagram. By understanding the energy band diagram, we will understand the energy. We will understand the physics of the device. By understanding the physics of the device, we will try to understand the device. So we need to understand what is the quantum dots, what is the resonant tunneling devices, and what is the single electron. So quantum dots are based on electron. In quantum dots, here we have a classical. You can see here we have a classical degree of freedom. Zero classical degree of freedom. Now, what is this classical degree of freedom and all? I will be discussing in my next slide. We need to understand it we need to understand it. What is zero? What is quantum dot? Based on zero classical degree of freedom. Resonant tunneling devices, they are based on 1 or 2 classical degree of freedom. What is this word degree of freedom? That I will explain it to. And single electron transistor, they are based on 3 classical degree of freedom. Now, what are this degree of freedom and all? If you are moving from a vacuum tube, then physics of the vacuum tube is different, physics of the PN junction diode is different, physics of a transistor is different, and physics of field effect transistor is totally different. You know the difference between field effect transistor, we know the difference between the BJT, you know that FET is a voltage control device, and diode is a, excuse me, hello, Sapna madam, are you able to hear me? Hello?
Yes, sir. No problem. No issues, sir.
Now voice is okay?
Yeah, it's audible, sir.
So there are three. Now what we need to understand, what are these degrees of freedom? We need to understand this device, because when you move from one device to another, totally the physics will change, and since the physics is changing, we need to understand that. So moving ahead. Now here comes the quantum well and confined state. Let us try to understand that how these devices are working in the quantum range, and this nano devices like single electron, and they work on one basic principle only. So that principle we need to understand. Like PN junction works on one principle, FET works on one principle, transistors works on some principle. So this particular quantum devices will work on certain principle. So we will try to understand that principle, and then we will try to understand the degree of freedom also. The band structure engineering of artificially created rare material as the new generation of a semiconductor device. Okay, these are basically the material. These are basically the material. These are basically the devices that are created using some artificial material. So they are basically quantum well structure, and their operation and the performance is controlled by quantum effects. For example, quantum well laser and high electron mobility transistors are well developed quantum devices. Now we need to understand each and everything. These are the slides I am reading, but I will try to explain our diagram also. There are two material 1 and material 2 represent a well and by sandwiching a narrow band gap crystal or a semiconductor with a wider band gap or semiconductor with a wider band gap crystal. Now coming to this, here any nano devices is based on this type of a structure. The structure is what? This is a material with a high band gap, and this is a material with a low band gap. This particular material is with a low band gap, and this particular material is with a high band gap. Before explaining this thing to you, I will try to explain the p-n junction diode. Okay. This is the p-n junction diode, which we are very well acquainted, and we have studied p-n junction diode in our engineering, all electronics engineer has studied this p-n junction diode. So in the p-n junction diode, what is happening? These two different materials, p-type material and n-type material, they are coming together, and they are forming some band gap. This is called the band gap. This is called the conduction band. This is called the valence band. This is called the conduction band. So here there is some sort of band gap. After two different materials come together, there is automatically a band gap created. This I am explaining. To understand. So this concept I will take it to the quantum well. Then this is the concept that I will take it to the quantum well. Now this is the p-n junction. When p-type material is coming in close proximity with the p-type material is getting connected with the n-type material, there will be some band gap created. This is the band gap created. And if you apply the forward bias, the band gap is very well understood. If you apply the forward bias, this band gap will get reduced. If you apply the reverse bias, this band gap will increase. I hope you understand this thing. Now we will move to our quantum device, our nanoelectronic device. Now here what happens? This is one material, this band gap. Let us see that this is one material with one band gap. This is another material with another band gap. Now this is one material with one band gap. Now what are the materials that I will tell you? This is one material, either name it as a material, and this is one material with another band gap. This is the band gap of another material 1, and this is the band gap of another material. Here when these two are coming together, what are that material? These are the artificially created material. These are gallium arsenide, we can say the material 2, and this gallium arsenide as the material 1, and again the same material. Material 1. When these are coming together, when these materials are coming together, there is what I told you in earlier slide, quantum well are formed by sandwiching a narrow band gap crystal or a semiconductor with a wider band gap. So this is the wider band gap material, this is the narrower band gap material. When these materials are coming together, they are creating this is with a lower band gap material, this is a higher band gap material. They will create one sort of a potential well. This is called a potential well. So I hope you understand the concept of it, or we call it as sometimes it is called as a quantum well also, and sometimes it is called as a potential well. This will create a potential well. Now in our injection diode, we cannot have this potential well here. Why we cannot have a potential well? Because both are the silicon device. This is silicon with the p-type material, this is silicon with the n-type. We cannot create a potential well here, but here the potential well is created. This potential well is created here. This is that particular this thing we call it as a well, and this is the band gap of energy of one material. This is the band gap energy of another material. In this potential well, we have the energy level. We have the energy level, 1 energy level, 2 energy level, 3 energy level. And imagine, and I try to understand one more thing here. We are talking about quantum devices. When we are talking about quantum devices, we are talking in the range of 10 raised to minus 9. When we are talking in the 10 raised to minus 9 level, we are talking in the 10 raised to minus 9 level, we are talking about phenomena that are happening at the atomic level. So when we are talking about phenomena that are happening at the atomic level or molecule level, we can discretize this energy level. 1 energy, 2 energy, 3 energy. This discretization of quantization of energy level. This quantization of the energy level is not possible in bulky material. Bulky material means what? Bulky material in the sense when p-n junction are there or FETs are there. No, I'm not talking about nano FETs. I'm talking about FETs or p-n junction diode or transistor. These energy level are not distinguished, or these energy level are not quantized. Since these energy level are not quantized, we combinedly call it as a conduction valence band. Whatever the energy levels here, the energy level concept is very important to understand the quantum device, to understand the nanoelectronic device. So this energy level, whatever this combined energy level, we call it conduction valence band. And whatever the energy levels are, whatever the energy levels are in the valence band, is the conduction. We call it as a band of energy, and whatever it is above the conduction band, we call it conduction band energy level. But this is not the case this is not the case. This is not the case in a nanoelectron device. Here the energy levels are getting quantized. 1 energy level, 2 energy level, 3 energy level, and 4 energy level. These energy levels are getting quantized. Now what will happen if the energy level are getting quantized? Once the energy level are getting quantized, once the energy level are getting quantized, once the energy level are getting quantized here, if the same energy level is here, before going into this thing, let me discuss about the C. When we apply reverse bias to a zener diode, we see a current flowing into the actually, if we apply a reverse bias to any PN junction diode, there should not be a current flowing. If you apply forward bias, then only there will be current flowing. But how the phenomenon of current flowing in the reverse bias can be explained using a zener diode? The phenomenon of current flow in a zener diode, even though zener diode is reverse bias, the current is flowing into the zener diode. But actually, it should not because it's a reverse bias. Our classical physics says that current will flow through PN junction only when it is a forward bias. And when it is a reverse bias, there will be no current. But in the case of a zener diode, what we will see, we apply a certain voltage, when the reverse bias is too much, then the current will start. Now why the current starts flowing here? Because see, at this point you can see, suppose this is a zener diode. If you are extending this band gap, and if you keep on extending this band gap, this energy level will meet with this energy. This energy level will meet with this energy level, and as per the Pauli's exclusion principle, electron can move from one energy level to the another energy level. Electron are free to move from one energy level to another energy level. So here the phenomenon that is happening is not crossing the barrier, but tunneling the barrier. The band gap is so much reduced that electron will not cross the barrier, electron will tunnel the barrier. Same thing will happen here. Now here what will happen, when we apply there is a potential band here. If you take an electron to this level, it will not cross the barrier. Here one thing has to be understood in nano devices, the electrons will not cross the barrier. As in PN junction diodes and all these things, when we electron will cross the barrier, and when we apply a reverse bias, electron cannot cross the barrier. But in this case, electrons are not crossing the barrier, but they're tunneling through the barrier. This is that barrier. Electron will tunnel through the barrier from this side to this side. And whenever there is a flow of electron from one side to another side, this is a forward bias. This is a bias.
The mic is connected.
From one side to another side. If you take an electron to this level, this particular energy, if it is available here, it will be freely moving to this energy level. And when it is moving freely to the another energy level, we say that electrons are moving to another energy. Current from one side to another. This is a phenomenon where so the quantum devices, the width of a quantum will determine whether the confinement is the width of a quantum well. This is the width of a quantum well, which decides whether the confinement can happen or not. Incidentally, the carrier experiences significant quantum well. Now, what is the level at which the quantum confinement can happen? The width is in the 200 angstrom range or less. The well there will matter as the properties of the microscope. In this particular range, the quantum confinement. So now what happens? The width L, this width L is shorter than the mean free path of the electron. This width L, this width of the well is shorter than the mean free path of the electron. Now, what is the meaning of the mean free path of electron? Every electron, it travels in a p-n junction or all these things. If you see, the electron travels from p, the electron will travel from one from p type to the n type, or from n type to p type. Okay? When we apply a forward bias, it will follow some path. It will not directly go to the other side. It will follow some path. It will follow some path, and that path we call it as a mean free path. It will not directly go. It will not directly go towards the electron will not directly go from n type to p type. It will follow some path. That path we call it as mean free path. Now in a that device size itself, the device size itself, this is the mean free path of the electron. It is less than the mean free path of the electron. With n is shorter than n is shorter than electron is likely to travel electron confinement. Electron confinement means what? Electron will move from one place to another, not in the path, but in the that type of transport we call it as a balancing transport. That type of transport we call it as a balancing transport, and it will not move anywhere. It is said that it will be traversing from one place to another place without any now here, what happens is the confinement of the electron is happening. Confinement of the electron is happening means what? The device size itself, device size. Consider this as the device size. This as the device size is the length of the device. It is lesser than the mean free path of the electron. Concept of the mean free path is clear to you. Mean free path, electron, like we move from one. Like if I wanted to walk from here to another place, so I will not jump to that place. I will walk. So that particular my that walk or that particular my walk is particular my walk will be something possible. Centimeter is there or 2 centimeters, whatever it is there. That steps only I can with that step only I can move from one place to another. I cannot jump from if I wanted to go from one place to another place. Suppose 1 kilometer I wanted to travel. I will not. I will from 1 kilometer I want to travel. I will not hop 1 kilometer. I cannot jump and go to the destination. If the destination is at 1 kilometer, I have to walk. That walk, particular that my walk is confined. That particular walk is suppose that if I take one step, while walking, distance between my one step and to the another step is suppose 10 centimeter. Suppose 1 feet. 1 feet. It will be 1 feet. So that I will maintain that 1 feet and I will reach 1 feet. Now imagine if that 1 feet itself is getting reduced, so I will get confined. If that 1 feet eventually is getting reduced, electron it is moving from one place to another. It's not hopping. It's not going directly. It will move in a certain mean free path. It will follow some mean free path. That mean free path, what is that mean free path? Follow the mean free path. So this mean free path is in the range of this lambda is equal to 3. This mean free path, it will do using this mean free path. But in a nanoscale, what happens is that the device size itself is less than the mean free path. When the device size itself is less than the mean free path, the device size itself is less than we say that electron confinement will make us to understand how the devices are quantum confinement of electron in a nanostructure. So as I told you, the scale size is like that. There is 1 degree of freedom, 2 degree of freedom, 3 degree of freedom. What is that? It depends upon the confinement of the electron. I hope you understand the confinement of the electron. So now electron confined in one direction. So now in any this motion of the electron, usually motion of the electron in x, y, z direction goes in a devices injection or a transistor or an array. In these multi devices, that x, y, z, because it's a band of structure, we are ignoring that x, y, z. We are only considering just the moment of the electron. But electrons are confined. And electrons are confined. The size of the device is, the size of a device, you have to take it to 10 to minus 9. If you are taking the size of a device to the 10 to minus 9 level, you will see that the level 10 to minus 9 well, or that is health of the well 10 to minus 9. is less than the mean free path of the electron. If it is less than the mean free path of the electron, it is electron confinement is happening in the quantum set. If electron confinement is happening in the quantum set, then we have to consider x, y, z direction. We cannot ignore the x, y, z. So either when we are confining the electron, either it can be moving in the x direction, y direction, or z direction, which we are totally ignoring in our multi devices. But here we cannot ignore that. Here we cannot ignore that because we need to. Here in our nanostructure, we cannot ignore that x, y, z direction of the motion. Now, depending upon this x, y, z direction of the motion, if electrons are confined in one direction, we call it as the quantum set. Electron can easily move in the two dimensions. They can be moving in the x or y direction. If electrons are confined in two directions, then we call it as a quantum bias. So here electron move in a one dimension. If electrons are confined in three directions, then we call it as a quantum dot or zero dimension. Now the question comes how in a quantum dot, if electrons are confined in three directions, how it is moving from one place to another. So we will say that electrons are hopping from one place to another. These electrons are hopping from one place to another. That means what? Electrons are hopping from one place to another. If an electron finds energy level, the same energy level in other side, that means on the material side, it can easily. So these are the concept of quantum. Degree of freedom, and based on this degree of freedom, we can have a device which are based on quantum wells, we have a device which are based on quantum wire, we have a device which are based on quantum. We'll go next. So there are two effects that are very important while understanding the nano devices. One is the quantization and another is the tunneling. Strongly influence the flow of electrons in nano devices. The tunneling can only occur and charge can flow over the plane only if there is an unoccupied quantum energy level in the well at an energy level that matches one of the occupied energy levels of the source. Now here we need to understand how electron can tunnel. How an electron can tunnel. That is another barrier. Electron can tunnel from one barrier to another barrier. Electron can tunnel from one barrier if it finds empty energy level. Same empty energy level on the other side. If it doesn't find the same empty energy level on the other side, it will not be able to. That is the function of the tunneling. Particular tunneling diode and all, Zener diode and all this. Zener diode cannot be explained using the classical. We need to understand quantum physics to understand. We need to understand quantum physics phenomena that are happening here. Somebody actually device forward bias and current flow. And if a device is the reverse bias, current doesn't flow. In your Zener diode, when we are the reverse bias, current flows. How it is possible? Electrons are tunneling from this side to this side. That is the reverse bias. There will be some energy level. There will be energy level, unoccupied energy level at this point. Electron will not drop the barrier. It will tunnel the barrier. Why is tunneling the barrier? It is tunneling the barrier because it will find same energy level on other side. Same energy level. I will discuss it next time. Suppose it is energy level ready. The same energy level that to an unoccupied energy level if you find it. We are applying the forward bias and reverse bias and the occupied. When this energy level and it comes in this energy level, find the unoccupied energy at this time that is tunneling the barrier. And we will say that electrons are not crossing the barrier but they are tunneling the barrier. Tunneling can occur, charge can go towards the plane. We have the four plane concept here also. Now, coming back to the electrons and electrons started from 1960 into the 1980s, going again into the electronics domain and the particle electron. Here, photonics also had one of the technologies that is fiber optic, that was the planar wave guide, that was the optical circuit, that called as photonic system. It is called as photonic system. That is the way it can happen. Now, so Mandeep sir had explained the nanophotonics and all these things, but what had made the research to be happen? What had why the research had happened into the direction of the nanophotonics and how it had helped electronics and nanophotonics, how these two things came together to try to understand it. Now, what is photonics? If we say photonics is the generation, transmission, modulation, switching, amplification, storage, and detection of light. The word photon denotes the fundamental unit of a light, which is both wave and a particle. So here the concept of wave and particle. The concept of wave particle. So we can say light as a wave and light as a particle also. Now, what is the nanophotonics? The area of a nanoscience called nanophotonics is defined as the science and engineering of a light-matter interaction. It is the interaction between light and matter. Like here, when we are talking about nanophotonics, nano.
ಆಮೇಲೆ ನೋಡ್ಬೋದು ನನ್ನ ಫೋನ್ಲಿಂದ ಹೇಳಿ ಸಾರಿ ಅಂತ ಹೇಳಿ ಸಾರಿ ಅಂತ ಹೇಳಿ ನಾನು ಇದನ್ನ ತೋರಿಸು ಬಂದೆ.
Hello. We are trying to, when we are talking about nanophotonics, we are trying to bring material, any metal or any material in a close proximity with the light. So it is an interaction, it's a light matter interaction. Matter is any matter, and it is the interaction between light and matter that takes place on a wavelength and a sub-wavelength scale where the physical, chemical or the structural nature of the natural or artificial nanostructure material controls the interaction. Nanophotonics actually is interaction between light and a matter. When there is an interaction between light and matter, that particular thing we call it nanophotonics. Now, interaction between light and matter, use the matter to transmit, generate, detect, and manipulate. So, for me, matter is a very big term. I will say, instead of matter, I will say matter. I will say material or something. It is made up of an electron. So, I will say that I care about electron. So, the very interaction between electron and photon. Here, I will not say that it is the interaction between a matter, as I made a statement here. It's a light matter interaction. To simplify, I will say it is an interaction which is as a photonics we are saying that the photon is a material, photon is a particle. Here in a material we are saying electron is a particle. So we can say the interaction between an electron and a photon. Very basic essence of nanophotonics is basically the interaction between electron and photon. Two very fundamental points. Photon related to the light and electron related to the material. Now here a very strange thing is happening. The strange thing is happening that I will discuss earlier. The photon wavelength is in the range of 400 nanometer to 700 nanometer. Now let's talk about the landscape and then you will understand that. So this is that electromagnetic landscape. You see here, this particular range is as I spoken earlier also, this particular range is the nanometer range, and this is the range of the photonics, or this we can say this is the range of the light. When we take, this is the nanometer range, this is the nanometer range, which is the range of the light. When we take our material, again coming back to the same discussion, when we take back material to the 10 raised to minus 9 range, material, it's the interaction between the electron and photon. Now it is fine, that light is in this range 10 raised to minus 9, we cannot do anything here. But when we take a material, any material, into the 10 raised to minus 9 range, now why we are taking material into the 10 raised to minus 9 range, or why we are taking device into 10 raised to minus 9 range, because if you don't take into the 10 raised to minus 9 range, you have to be with the IBM hard disk because of 5 MB in 1966, and how much efforts were required, how much efforts were required to do that hard disk. Okay. If we don't take the material into this range, we cannot go ahead further with our. If you cannot take the material into this range, we cannot take forward. We cannot take the advantage of the convergence of electrons. This is the range of the light. Now, this is the range of some material length. Suppose 2 meter, 1 centimeter, and all this. 1 centimeter, and this is a bucket. So these are the material, and these are the light. This is the material range, and this is the light range. This is the nanophotonics is the interaction between the matter and the matter. Nanophotonics is the interaction between a matter and a light. So as I told you earlier, matter is a very big term, light is a very big term. So I can say it's the interaction between any electron and a photon. So what will happen if the electrons and photons are interacting, and which we take the advantage of. So nanophotonics, we can see it in the mother nature also structure in the ring that is like which Mandeep Singh had already discussed. So, nanophotonics outline. So we can say it is an interaction between a photon-electron interaction. So when we are saying photon-electron interaction, then any electronic devices we see, it works. It is confined. If it is not confined, it probably may not work. Confinement means what? When we are trying to understand a p-n junction diode. P-n junction diode means what? We are confining electrons on the n side and both on the p side. And how they are confined? By potential barrier. If the potential barrier is not there, electron will move freely on the other side and holes will go from the other side. But we don't want that to happen. We don't want that. We don't want easy movement of the electron from one side to another side. So what will happen when two materials are coming together? Potential barrier will be created. Electrons are confined on one side, holes are confined on one side. Now we want this device to work. I am talking on a confinement. What is the necessity of the confinement? If an electron is confined in a p-n junction diode, electrons are confined on the n side and holes are confined on the p side with the help of a potential barrier. When they are confined, electron will not move because of the potential barrier. Electron will not move from n type to p type and vice versa. Okay. Holes cannot go from the other. Holes cannot go. So what we have to do? We have to apply to remove this confinement. We have to apply some potential. That potential will go forward bias. When we apply the forward bias, what will happen? Potential barrier will get reduced. The potential barrier is getting reduced, then electron will move from the n side to p side. If you keep on doing this, if you keep on increasing the forward bias, you will get more and more current, and at certain stage it will, and the certain stage it will enter into the saturation. Okay. So same thing is with the confinement. So electron photon confined. So that lead to the nanophotonics. Now let's explore optical wave, optical unit. So we have the optical unit wavelength in the energy, wavelength energy, and different name for the same information. For the photonic person, it is a wavelength, and for the physics person, it is an energy. So again, if you are talking in the terms of this physics person, energy is equal to h. If you have h equal to c by lambda. So here this is the longest wavelength. You can see here is the shortest. Now, quantum theory describes the light as a particle or a photon. According to the quantum theory, photon has an energy. It is having some energy. And the energy of the light is proportional to the frequency. The higher the frequency, the higher the energy of the photon. 10 photons have an energy equal to 10 times of the speed. Quantum theory describes the experiment to astonishing precision, whereas the classical wave description cannot. So this is the relation. Now where we are in the nanophoton, when we are in the nanophotonic state, we are talking in the terms of the wavelength. We are in the regime of the nanophotonics when we are, and you try to understand when we are in the nanophotonic state and when we are in the classical. When the use of the wavelength. Now what is the wavelength? As I told you, this is the shortest wavelength. This is the shortest wavelength, most energetic. This is the longest wavelength. So when we will use the wavelength as a scale, because we are talking of the feature size. When a feature size A, feature size means for any fiber or any material or any optical fiber is greater than wavelength A, is greater than wavelength A, so much feature size is greater than A, then we are in the classical optical. When it is A is equal to lambda, when the structure size is equal to lambda, at that time we are in the same scale, same length scale as the light, order of a classical optics and nanophoton, photonic crystal base and all this. Okay. Then when the feature size, again these are the very inorganic type of material. When the feature size that are much smaller than the wavelength, this is clearly the nanophotonic. So example, optical crystal, metamaterial, which are Mandeep sir and already discussed. Material where we don't depend upon the mother nature, we design a material to go to the output. This we call it as a nanophotonics. This when feature size is equal to the wavelength, we call it as a classical. This is the broader of a classical and nanophotonics. Now let us see what is the electron. We had started what is photon. The electron is a subatomic particle. Because why we are discussing an electron and photon? Because for me, at nanophotonics, what is important is the interaction between a light and a metal. So instead of discussing light and a metal, I am taking it to the level to a lower level, and I'm saying that it's not an interaction between light and metal. It's an interaction between photon and electron. We need to understand what is photon, and we need to understand what is the electron. The electron, Electron is a subatomic elementary particle that carries a negative charge. It has an intrinsic angular momentum of half integer. Spin is equal to 1 by 2. Now, if Pauli's exclusion principle, one electron can occupy one quantum state. Only in a one single energy level, only one electron can occupy. Only one electron. This is called the Pauli's exclusion principle. We have studied in our earlier classes also. So because of this, we have a periodic table. Because of this, we have a periodic table of the elements where the electrons are getting aligned themselves and according to the materialism. So what is a photon? Photon is an elementary particle that possesses both electric and a magnetic field that are governed by Taxonomy. It has the angular momentum of integer values spin is equal to 1. Photon do not interact with other photon, and so more than one photon can occupy the same quantum state. Now here we need to understand that photon do not interact with another photon, but electron, it is not the case with the electron. They will, when two electrons are brought together near to each other, they will either try to repel or they will try to balance it. So we cannot have two electron in the same energy level. But this is not the case with the photon. Photon don't interact with other photon, and so more than one photon can occupy the same quantum state. So this one piece of optical, that's why one piece of optical fiber we can put more than one frequency of a light fiber, and this is very important. This is how the internet gives us bandwidth domain and expansion across the globe. But we cannot do with this of copper. We cannot do this thing, and that's why we have these optical fibers and all. We cannot do this thing with the copper, because in a copper, if you put electron one after the next, electron will interact with the previous electron and it will give some difference. So electrons can occupy only one state, that will be the help of, because of the Pauli's exclusion principle, and this is not the case with the photon. Photon-electron interaction. Now we are to talk photon-electron interaction. We can classify the material, the transparent material. Light excites an electron count of one atom, which emits the photon that interacts with another electron. Photon moves at the velocity c, but extra time for the excitation emission slows the process down to the velocity. So we define the refractive index as n is equal to c. The refractive index tells us how light interacts with the material. Light interacts with the refractive index of a material tell us that how because we are studying the interaction of a light with the material. Light interacts with the material. The interaction is the refractive index. It also tells us how the wavelength changes. That means if a transparent material is there, if a light beam falls on it, if you see, because of the refractive index of the material, direction of the light will change. The opaque material. In the opaque material, light can be observed and emitted by a resonant electron and a photon interaction. Here, because in the opaque material, it will not allow light to transfer. Because light can be observed and emitted by the resonant electron and photon interaction. So in opaque material, light cannot pass. So electron and photon comparison, if you see, both elementary particle exhibit both particle and wave like. So electron and photon both exhibit the property of a particle and property of a wave. So with this wave particle duality, we will try to understand most of the phenomena that are happening at the photonics level. The propagation of a light affected by dielectric material because of the reflective. Propagation of the electron affected by a Coulomb potential because of the potential barrier and created. It will affect it. Propagation of a light is affected by a dielectric medium. That is the refractive medium. The refractive medium. But in case of the electron, it is affected by the help of the potential barrier. Now in a free space propagation, photon plane wave, this is the equation for a photon plane wave, and this is the equation for the electron plane wave, when we call it as a wave. So confinement is very important to understand the confinement, how the confinements are happening in a material side, and how the confinements are happening in the light side or in the photon side. So in the nanoscale confinement, I had told you about 1D confinement, 2D confinement, and 3D confinement. We are using this method to confine the electron. In case of a light, we are using planar waveguide because this is having a different refractive index. So light can travel through this. Light can internally reflect. We have an optical fiber 2D confinement. There is a 2D confinement, and we have a 3D confinement also. So this is the confinement of a light, and this is the confinement of the electron. both can come together and they will create something called a confinement of a light, result in the field variation similar to the confinement of the electron in the potential. For a light, the analogy of a potential where is a region of a high refractive index bounded by a region of a low refractive index. That means for the light, if this material is a high refractive index, this will be of a low refractive index. This will lead to the this will be bounded. This is the bounded by region of a low refractive index. Now confinement by various means. The electron, we have a Coulomb force, we have periodic potential, we have metallic energy. In a photon, we have total internal reflection, periodic dielectric, or a metallic confinement. So the total internal reflection, if refractive index N1 is greater than N2, the refractive angle can exceed 90 degrees. Light is confined with a high index region by the total internal reflection Snell's law. Here by the Snell's law. So photonic crystal, again, I will not go into here. I will not go into detail of the photonic crystal. But electron crystal, and this is the electron crystal, and this is the photon crystal. This is the electron crystal, and for a solution of a Scotland equation in 3D periodic Coulomb potential for the electron prohibits forbid the propagation of a p electron with energy within the energy band. Here, likewise, diffraction of a light within a photonic crystal is forbidden for a range of frequencies which gives the concept of photonic band gap. The forbidden range of the frequencies depend upon the direction of the light with respect to the photonic crystal. However, for sufficiently refractive index contact here exists the band gap. So here, there is some material arranged in such a way that it will be creating a band gap and the light will be transmitted. Okay. So I hope most of the things are clear. So we have the good nanophotonics market here. The photovoltaic, somebody had asked the question that where it can be used. So we have a market is also increasing. So this was my lecture on the nanophotonics. Now 2 minutes I will talk, as I told you, this particular understanding on quantum confinement, quantum physics will lead excuse me, will lead to our understanding quantum physics, and will lead to our understanding of quantum entanglement and quantum computing. I'll speak on quantum entanglement for a few minutes, and then I will wind up my lecture and I will open the session for question and answer. Now, what happens in the quantum entanglement and obviously, for understanding the quantum entanglement, we need to understand the double slit experiment. In the double slit experiment, what happens? In double slit experiment, when the electron is passed to a slit, it will create a pattern. That is called the interference pattern. But at the same time, if a wave is passed through the slit, it will create an interference pattern which will have a number of slips there. But it was observed that when electron is also passed through the slit, as usual, if electron is passed through the slit, it will create one interference pattern. And when the waves are passed through the slit, it will create a number of interference patterns which have high intensity, low intensity, and all. But when the experiment was conducted, and when they passed the electron through the slit, they found it out that electron is not creating one pattern. Electron is also creating a number of patterns with a high intensity and low intensity. This they were not able to understand, and when they tried to apply the classical physics and all these things, they were not able to understand. They went to the quantum physics and they understood that electron somewhere is behaving as a wave, and only the wave can create some sort of an interference pattern. Now, what happens here in the quantum entanglement and all? Since electron is behaving as a wave, this wave can be split into the two portions with a mirror, by keeping the mirror and all this thing. If it is split into the two portions, same wave is split into the two portions, and one is transmitted in one direction and another is transmitted in another direction, but since they are related to each other, as I told you, I will not talk here about wave, I will not talk here about material, I will talk here about electron, and I will talk about photon here. Entangled with each other. They are entangled with each other. Since they are entangled with each other, since they are entangled with each other, you see any phenomenon, any change happening in one photon will reflect into the another photon. You need to sometime, since there not much time is there, sometime if I somewhere if I get a time, I will talk more into the quantum entangle. But you try to read into this quantum entanglement, quantum computing, and all these things. I know that you have not understood what I am talking for photon, how it gets split into the, but you try to read into this. If you try to read into this, you will you will definitely understand what is this, how the quantum physics is applied, how quantum physics is applied to understand that phenomenon. And the coming era is of quantum computing. The coming era is of a quantum confinement. Coming era is of a quantum entanglement. You try to read into this direction. But when you try to read this quantum confinement, quantum entanglement, and all, keep three things in the back of mind: that their classical physics will not work, their only quantum physics works. Quantum physics again works onto the three principles, and the three principles are that wave-particle duality, Heisenberg's uncertainty principle, and quantization. These are the three things on which quantum physics works. These are the three things on which quantum physics works. Now the question comes here. As I told you, there is a classical physics, there is quantum physics. There is one more physics called metaphysics. I will say that you try to read onto the metaphysics, and you will try to, if you try to read more onto the metaphysics, if you try to read more onto the quantum physics, more and more mysteries that are in this universe will be getting disclosed, and you will try to know more and more about phenomenon that are happening. Now, this classical physics is something which is a certainty that yes, these things are there. Quantum physics says, quantum physics, as I told you, it works on the principle of wave-particle duality. It is saying something which is probability. It is saying yes and no. Try to understand. I don't have a diagram here, otherwise I can draw. If we say a classical physics, it says yes, the things are there. Quantum physics says yes and no, probability of finding the electron, probability whether the electron is wave or electron is a particle. Then what is the metaphysics? It is saying completely no. Completely no in the sense, I don't know myself, I don't know anything in the universe. So this is a pendulum sort of. We have to move this pendulum from classical physics to the metaphysics. This pendulum is somewhere in this pendulum we have to move from a classical physics to a metaphysics, where the quantum physics will help us to move this pendulum from a classical physics to a metaphysics. So we can say that we are in the range of we are in the yes. Now we have to move towards the no, which is unknown. So this classical physics will help us to move from the known to the unknown. Still, it is said that somewhere I was reading. It is said that with all the universe, with all the PhDs and with all the Nobel Prize, Nobel Prize winners and all these things, we know only 4% or 5% of the universe. We can exaggerate and say we know only 10% of the universe. So remaining 90% of the universe is unknown. This 90% can be known to the man if we take a help of quantum physics, and if we move towards the unknown side. This graph will move towards this graph which is on the 10%, which is known universe, and which is 90%, which is unknown. This quantum physics will help us to know the unknown, and we can see this graph will be that known will become one day, the known will become 100%, and unknown will become 0%. So at present we are in the stage where if you try to understand the various phenomena, there are some phenomena which are unanswered. This can be answered using the quantum physics. So we are at the stage where 10% is only known to us, still 90% is unknown. We have to move from 10% to 100%, and the quantum physics will help us in moving from a 10% to the 100%. And that unknown we call it metaphysics. I hope it is clear to you. I hope my lecture was lecture had given a new idea that to understand about quantum, and to understand about quantum physics, to understand about the light matter interaction, why we had moved from why there is a need for moving from there is a need for moving from vacuum tube to the nano devices. If we don't move to the nano devices, we cannot fabricate the devices which can carry in our pocket. So Nandini ma'am, I'm done with my presentation. If any questions are there, I will be very happy to answer the questions.
Yes, sir. First of all, thank you, sir. Thank you for your presentation. Sir, there is a question from Abhijit that regarding quantum dots. Where exactly the quantum dots are used and what are the application? He is interested in doing research about it.
Very good. Yeah. So Abhijit, you might have seen quantum dot TVs and all of that are coming. LCD displays are and all these are LCD displays nowadays. LCD LED displays. They are, if you may see in advertisement on all this thing, they will be mentioning quantum dot. They don't understand anything. And those who are in the advertisement and all this thing, they may not be understanding what is a quantum dot. But you might have seen that word quantum dot is used somewhere in that when they are advertising some Sony or Samsung, they are advertising their TV. They're telling that our LED panel is a quantum dot. It's a quantum dot technology that we use. So there are so many applications, and the top of my mind it is coming that LED TVs and all these. And if you wanted to know more detail onto this thing, you can make a note of this thing. You can make note of the website nanohub.org. NANO nanohub HUB nanohub.org. This is the website. It's a very open website where you can also contribute. There are some simulation tools and all available where you can do the simulations at the nano level, material level and all this thing. And since this field is open to all, it is not confined to our electronics. Since I discussed more application related to the electronics, it is not confined to the electronics. It is mostly confined. It's not confined to the electronics. It's confined to it is open for all branches of the science. It is open for all branches of the technology, medicines, and all these things. So you will find in that nanohub.org because it's mostly related to the material research. It's mostly related to the material research. So you will find so many work happening in that direction. You can come across with the good lectures also. You can understand what is the quantum entanglement there also by looking into the video. I not much talk onto the content, but you try to read onto this thing because this is the upcoming area. So to answer your question, quantum dots and all this thing are used in quantum dots and all this thing are used in the LED TVs. You can browse and you can check it out more into detail.
Yes, sir.
Next
Thank
question.
you, sir. Sir, from Mahesh, what are the nanophotonics developments in India? Maybe he's asking about the areas of development.
As our Mandeep Singh had said, nanophotonics, there is quite a good research going on to the nanophotonics domain and all this thing. Specifically, this lecture series is arranged by the people those who are working in the nanophotonics. Mandeep is there. Tomorrow also will be hearing a lot onto the nanophotonics. There are the experts into this thing. We have a biomedical field. We have a MOEMs which we'll be seeing in our next lecture coming up. There are lot of applications where we will see that nanophotonics is coming up. It will be if you are listening throughout to this lecture series, you will be coming across many applications. As Mandeep Singh had also said, Mandeep sir had said. Tomorrow, today, Payal madam will be talking. Sneha madam will be talking, and we have a very renowned professor from IIT Kharagpur who will be talking on biomedical imaging and sensing. Shrikant sir is there. He will be also talking. So there are a lot of applications which will be coming, which will be listening to in our presentation. So I will not remove that. I will let that curiosity remain, and which you will be able to hear more onto when the speakers are.
Yes, sir. One last question from Dr. Neeta. Sir, regarding nanocopper, where exactly they are used? Nanocoppers.
Okay, nanocopper. I search nanocopper and all this thing. See, when we try to understand this nanocopper and all this thing, the property of the material, copper, the property of the copper material, they are changing. It is changing. So this can be used in a bulky bonds sort of things are there to manufacture. See, and nano copper as such is copper properties will be changing when we are going at the nano level. This change in the properties, we need to understand what are the change in the properties that are happening. This change in the properties can be utilized for the benefit of the mankind. So it is like we have some we have some conducting material. So there is a possibility that conducting material property may change and it may become a superconductor at that level. So it can be used in that in that application also. Thank you.
Okay, sir. Thank you so much, sir. Thank you, participants. And yeah, we are sorry for the disturbance caused. However, we are going to rectify that for the next coming sessions. Thank you. We'll join by 2 o'clock. Thank you, sir.